And what is it up to? Well, the EVLA is leveraging the existing infrastructure that's there. So we have 27 radio telescopes. If we were to rebuild those from scratch, they would cost between, depends on your mathematics, $3 and $5 million a piece to build from scratch, and then you have to do all the other work that needs to be done. So we're basically keeping the existing infrastructure, the antennas. Many of you probably know that these telescopes ride on track, literally railroad track, that we got from railroads when VLA was built in the late 1970s. And there's a Y, so there's 3 big arms of track. We're still using that, and of course our people and our basic facilities, but we're stripping out all the electronics. It's the electronics that sets the fundamental sensitivity of the telescope and our ability to see fainter, further, and better. So we're rebuilding all of that with a new correlator. The correlator is the supercomputer that brings all the data from the individual telescopes together and turns it into images for us. It's basically a special purpose supercomputer. The receivers that actually detect the radiation. Right now we have much of the frequency band between 1 and 50 gigahertz filled, but not all of it by any means. EVLA will cover all of that regime continuously. Fiber optic data transmission system, very high quality. Digital electronics, and of course the bane of all projects, software. So the EVLA will basically renew the VLA into a new instrument, and that's part of what makes us think about, maybe we rename it at some time in the not too distant future. When might we do that? Well, that's up to people far higher in the food chain than me, but I think the most likely time would be when the correlator is delivered. The telescope is right now, we're about halfway through renovating the antennas, and one of the wonderful things that the staff in New Mexico are doing is they are keeping the VLA operated for the astronomical community as the telescope is converted from the VLA to the EVLA with very little downtime, which is quite a challenge. When the correlator comes in, the capability of the telescope will take a big leap. The correlator allows a lot of things, a lot of science to be done, a lot of ways to operate the telescope that aren't part of what we can do right now. And I think that's, if I had to guess, I would guess that's when that's going to happen, when we might consider rename. Whoops, can I go the wrong way? Oh no. Every new telescope has a set of science themes that it attempts to address, right? There's no way you can sell a new telescope unless you have a set of science goals that you're going to attempt to achieve. And of course those are important, and a lot of thought goes into those. But in all honesty, serendipity is a very important part of science. And typically, you get 10 or 20 years down line from when you first started using the telescope in new ways, and you find that a very large fraction of what you discovered you didn't anticipate. So there is certainly that as well. I heard a wonderful talk by the gentleman who was the director of the Keck Observatory for a number of years. And he, after Keck came online in Hawaii in the early 1990s, they were the first telescope of that new size, right, 10-meter diameter, new class of optical telescope. They got there well ahead of everybody else, and so they swept a lot of low-hanging fruit, low-hanging scientific fruit off the table, right, irritated everybody else, but that's what happens when you get there first. So they discovered many wonderful things, many interesting things, and Director Fred Chafee gave a talk about what the top 10 discoveries by Keck were, and exactly 2 of them had been included in the science case for building Keck. And that's not unusual, that's typical. But nonetheless, we have science things. We know, for example, that radio telescopes are especially good at understanding and measuring the structure and strength of the cosmic magnetic field. This is something that radio astronomy does very, very well. Radio astronomy is also very good at observing what we call the obscured universe. So these dust-enshrouded regions where stars are born and planets are born and where supermassive black holes live at the center of our galaxy are places that radio astronomy can see into that optical cannot. Optical and many other wavelengths cannot. Radio is also very good at following the rapid evolution of energetic phenomena. And this is a particular object called a microquasar. This is probably too small for you to read, but this top image was taken in March of 1994, and this bottom image is in April of 1994, so this is only a month, and this is the observed evolution of a so-called microquasar, a very energetic event observed by the very long baseline array. The evolving universe is very important, studying the formation and evolution of particularly the first stars and galaxies. And this rather unimpressive image here is unimpressive because that radio source represented by these contours is enormously distant. For those of you who like redshift, this is at a redshift of more than 6. You know, we're talking billions of light years away from Charlottesville. You got to think local. Local.
What's happening in that upper right-hand diagram?
Let me go back up. There's been an outburst. There you go. There's been an outburst, and so these two objects are separating now at a very high rate of speed. And these are the kind of sources, these microquasars, as well as many other supermassive black holes, give rise to the so-called superluminal expansion, which is a fancy word for they look like they're going faster than the speed of light, which of course troubled people for a long time, still troubles them in certain ways, but we believe it's largely an artifact of geometry. We don't think Einstein's in trouble. Well, this is the EVLA correlator. This is the supercomputer that is being delivered to New Mexico to process the data from the improved Very Large Array. This is the principal contribution of our colleagues in Canada, and in particular, two gentlemen, Brent Carlson and Peter Dubney, who work at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia, have developed this technique that's called WIDAR, which stands for Wideband Interferometric Digital Architecture. You know, people spend hours thinking those things up. You know. It's a good one. It's an innovative method for doing the digital correlation of very wide band signals from a radio interferometer. So the EVLA looks at a very large piece of the spectrum, 1 to 50 gigahertz. It's very wide band. And so the correlator has to have special capabilities that, quite frankly, our correlator at the BLA right now does not. This is what it will literally look like. It's a computer, right? So it looks like racks of equipment and racks of chips. And that is what it is, but it's custom chips, carefully designed to do the special processing needed to bring data from the elements of an interferometer together to create images. This is a look at some of the boards, right? This gives you some sense of the system input bandwidth. So how much data can the correlator deal with going into it? And the answer is about 3.8 terabits per second, which is equivalent in very round numbers, right? We're astronomers, to the amount of data that's on 160 DVDs of the typical size right now. So it's putting that much data per second into the correlator. That's what it's dealing with. And it's got 40 times 10 to the 15th operations per second. So 40 followed by 15 zeros operations per second. And it's delivered in quadrants between 2008 and 2010, basically about a quarter of it at a time. And it completely replaces the current VLA, Very Large Array, and Very Long Baseline Array correlators. It's a wonderful piece of technology in the service of science. So that's EVLA. That's the first of these radio astronomy futures I wanted to talk to you a little bit about. EVLA is about halfway there now. The total project cost is about $50 million, and we're funded at the level of roughly $5 million a year. It takes a decade. We're about halfway through. It'll be finished in 2012. And again, I think one of the really wonderful successes of the project is that the Very Large Array is up and doing science through the whole thing. So scientists who use the Very Large Array right now are actually also using the EVLA, because half of the array has receivers that are of the quality for the EVLA, which is a factor of 10 to 100 better than what we have now.